Back again. All right, so we're in phases of water. Please make sure that in this packet you're on page 5 if you've got the packet. If you're not in the packet, maybe you printed out this page, or maybe you're just simply looking at it through the Google folder. All right, so let's talk about phases of water. I also want you to be on page 1, properties of water, so that if we need to reference that, we go back to there. All right, so here we go. Water, the only substance on this planet that exists in solid, liquid, gas. And if you're curious, I'll refer to it as agua or shue, depending on what language you are, because it's just, I appreciate all the different ways to say water, because water is that important. All right, so we've got 3 phases. All right, the word phases and phase changes are going to be very important to delineate as we discuss this topic. They are different in how they behave within the phase curve diagram, but it's going to be important to understand that phases are all liquid, all solid, all gas, okay? So when we're talking specifically about water, we're talking about ice, we're talking about liquid water, we are then talking about water vapor. Those are the phases. Those phases exist from 0 degree, or at 0 degrees C, 32 degrees Fahrenheit, and lower, okay? Liquid water exists from 0 degrees Celsius, 32 degrees Fahrenheit, up to 100 degrees Celsius, 212 degrees Fahrenheit. And water vapor exists from 100 degrees Celsius to 212 degrees Fahrenheit and up. In each of those, you are a phase. Between them, going from ice to liquid water, is a phase change. From liquid water to water vapor is a phase change. Something special happens right at the 32 degrees Fahrenheit mark, 0 degrees Celsius mark, and at the 100 degrees C, 212 degree Fahrenheit mark. There's a different thing that takes place there. But at those ranges I'm just referring to, those are the phases. All right, so going from a solid piece of ice to liquid water is called melting. We need to input from a heat source 334 joules for every gram of ice in order to get it to melt at 32 degrees Fahrenheit. So if we're putting energy in at 32 degrees Fahrenheit and we are putting in 334 joules, joules is the unit of energy, per gram of water, ice, we will change that ice into a liquid. We call this value, with this unit, the latent heat of fusion. Okay? So latent heat of fusion refers to when we are adding and removing heat at the solid to liquid borderline, between the two of those. Okay? So, again, latent heat means you are adding in energy to change what it looks like. That's why it's called a phase change. There is no change in temperature at a phase change. All of this energy is going to change what it looks like, the state of matter that it's in. Okay? Now, going from liquid phase to gas phase, at the 100 degrees Celsius, 212 degree Fahrenheit point, we will be adding in 2,260 joules per gram to change 1 gram of liquid water to 1 gram of gas, water vapor. Now, we call this the latent heat of vaporization. Now, if we were to extract that amount of energy for every gram of water vapor gas, we would condense, we would make that gas go back into 1 gram of liquid water. Take a moment to put heat of vaporization and heat of fusion into your own words. Here, we also have a diagram for you to reference, maybe when creating your discussion. So go ahead, pause the video, we'll come back, and we'll talk about these diagrams. All right, so if we're looking at this diagram and we're talking about how that phase is changing, we're going to see that we may have on either extreme, we've got our solid, we've got our gas, and in the middle we've got a liquid. If we add 334 joules per gram at 32 degrees Fahrenheit, 0 degrees Celsius, we'll change 1 gram of ice to 1 gram of liquid. In order to change that 1 gram of liquid to 1 gram of water vapor, we have to add 2,260 joules of heat energy to that gram to change it into vapor. The opposite is true. If we are going to remove that heat, so if we remove 2,260 joules from 1 gram of water vapor, it will condense to 1 gram of liquid. Continue that sequence. If we take that 1 gram of liquid and we reduce 334 joules per gram, we will take that 1 gram of liquid and freeze it into 1 gram of solid water ice. This gives you a visual cycle of this graph here. For this graph only right now, we are saying we're going to follow this graph as if time is increasing in this direction, and as time is increasing, we are adding heat to the system of water. Now, to kick us off, here we are starting at the beginning. We have solid ice. So as this solid ice warms up, its temperature does change because it's in a phase, not a phase change yet. So as we are increasing in temperature, let's zoom in a little bit here. So as this solid ice is given heat, it increases until it reaches a phase change temperature, 0 degrees C. At that 0 degrees C, every gram of water needs to gain 334 joules per gram. In order to melt from solid to liquid. Okay? Once all of the melting is complete and everything is now liquid, that liquid in its phase can begin to increase in temperature again until we reach the next phase change temperature. So at this phase change, liquid now has to undergo a change to water vapor, a gas. The same idea occurs. Over this time, which is more time and more energy, will be required to change all of this liquid water into all gas. Each gram of liquid water will require 2,260 joules per gram in order to change out into completely gas. Once you get everything into the gas phase, you will continue to increase in temperature. So let's review the names of the phase changes. Melting occurs here, where there is no phase change, or where there's no... It's a lot of beeping today. All right, so that melting is not seeing a temperature change because all the energy is being added in to change it to liquid. If I were to ignore the rest of this for now and just focus on the freezing, I would say that once liquid decreases down to 0 and energy keeps being removed at 334 joules per gram, like your freezer on your refrigerator, it starts to freeze all of that liquid by removing the energy for every gram of liquid. And once you are completely solid, that temperature can continue to decrease in the freezer. So ice can be colder or warmer, but still below freezing. The idea applies here for our latent heat of vaporization. We will get evaporation into gas if we're adding, and if we're cooling our gas down here, we're removing heat and maybe condensing it back into a liquid. Of course, it's not going to work when I need it. All right, let's move on to here. So water with evaporation. So we talked a little bit about evaporation during porosity and permeability and the different variables that are going to impact how quickly or how slowly water will evaporate. So here are several conditions that are related to what you would do if you wanted to speed up the evaporation process or reduce it. So this is showing how we might cover it to reduce evaporation. Maybe we'll open the container to increase it. Maybe we'll add heat, and then maybe here we'll add even some wind to it, okay? Ooh, thought we'd get away without one of those. All right, that's right, we don't edit here, this is raw. All right, so let's move on to another aspect, specific heat, but you know what, before I do that, let's go to the reference tables so that I can introduce to you more in detail the fact that if we have melting, you don't have to memorize that number, but you do have to memorize where it is and how to use this number. All right, so we have for melting, heat energy gained, so we're putting heat into the system. Heat energy released, we're pulling energy out of the system. Both the same amount, but either we're adding or subtracting. If you'd like to, you can put a plus symbol here, you can put a minus symbol here. Now, heat energy gained during vaporization, we've got that value, we're adding heat to the system. And this one, we're removing heat from the system. And don't forget our little density of water at just a smidge below 4 degrees C, the density of 1 gram per milliliter. All right, let's scroll this up. Hopefully you have that available too. And let's go into talking about specific heat. So specific heat likes to talk about phases. So we talked about in the previous section that phases can increase in temperature when given heat energy. But at the phase changes, that temperature change does not exist because the energy is all going to change what it looks like. So let's talk about what happens during the solid, the liquid, and the gas phase for an increase in temperature. So specific heat, let's actually understand what the unit is. This strange unit of joules divided by grams multiplied by degrees C. That looks complicated. It's okay, we'll figure this out. It's not as hard as you think. So joules, I introduced to you, joules are the heat energy unit, okay? It's needed to raise the temperature of 1 gram of a substance 1 degree C. So let's take an example from the chart and use this explanation of the unit to make sense of what this means for an object. So we probably all know what copper is. Okay? Copper in a solid state requires 0.38 joules of heat to raise 1 gram of copper up 1 degree C. So it takes very little heat energy of joules to raise 1 gram of copper 1 degree C. If you need to, rewind that and listen to that one more time. Liquid water, which is in the liquid phase, requires 4.18 joules of heat energy to raise 1 gram of liquid water 1 degree C. So if we look at these two things, liquid water versus copper, it takes more energy to raise 1 gram of its substance 1 degree C than copper. So the higher the number, the more energy it takes to raise the temperature, which makes it harder to heat. It also means that it holds on to that heat and retains it, and it cools down more slowly if it's a high number. If it's a low number, it heats up quickly and it cools down quickly. Let's talk about how to utilize these values with a question. Pause the video now, try to sort out the solution, and then we'll come back and we'll share it. Okay? All right, so this says how much energy will take to heat up 100 grams of liquid water. Okay? Well, based on our specific heat values, we see that liquid water, and by the way, this is the same reference tables diagram that I showed you before, and hopefully this will line up better. There we go. Liquid water takes 4.18 joules per gram to raise it up 1 degree C. So if I want to raise this 100 grams up 1 degree C, I have to figure out how many joules of energy. So when we see energy, we're thinking joules. Okay? So down here I've got 100 grams of H2O. It's kind of hard to fit this in here, but you would maybe do like subtext for H2O. Okay? All right. Now, we know that it takes 4.18 joules per gram degrees C to raise it up in temperature. So I'm going to figure out that this is my unit conversion. Oop, there we go. So 4.18 joules per grams degrees C. All right? So now, let me erase this. If I want to know how much energy it takes to raise it up this 1 gram, or this 100 grams, 1 degree C, I'm going to multiply these out. So I should get 418. And for our sake right now, I'm going to say that we are going to just eliminate this whole unit at the bottom and this unit here, because we're saying we're only raising it up 1 degrees C. So ultimately, this unit will cancel, but 100 times 1, just it becomes 100. Right? So 100 grams will need 418 joules of heat energy to raise up 1 degree C. Try out the iron one again if you didn't take on these two originally before pausing the video and you only tried on the one. So go ahead and pause. I'm going to erase this. Go ahead and pause and bring it up in just a moment. Now, if you're back with me, again, how much energy we're dealing with, the amount of joules it will take to heat up 100 grams of iron, 1 degree C. So again, we've got 1 degree C that we're raising this thing, 100 grams of, in this case, I'm going to write Fe for the elemental symbol of iron, and we need the specific heat of iron, which is here. The board is not lining up. Must be getting a little tired today. 0.45 joules per gram degree C. Right? So if we go through and we cancel out the units, we have 100 times 0.45 joules. So we should end up with 45 joules of heat energy. So this one here was, so the original first question was 418 joules, and the iron ended up being 45 joules. This gives us proof that it takes more energy, in this case 10 times, almost 10 times more energy to heat up 1 gram of liquid water versus heating up 1 gram of iron. you may realize that these situations occur in nature because let's say you're at the beach and the water is cold but the beach sand is hot. Well, the beach sand is mostly made of granite and the ocean, liquid water. So the beach has a lower specific heat, so it will heat up faster in the sun, but the ocean water will not. Reverse, at nighttime, whatever heat has been gained by the ocean will slowly cool off, but that beach sand will cool very quickly because it doesn't hold on or retain that heat as well. Okay. So now let's go into our independent practice. Again, we want to be in this folder. Grab your phases of H2O specific heat guided and independent practice. Go ahead and grab your access points and let's take a moment to pause the video and answer this question here so that we can continue our understanding. All right, so now that you've had an opportunity to read through this question, you've been able to hopefully annotate the question, go back in your notes, refer to your notes, check your reference tables in case you needed it, maybe even took some time to memorize maybe where these things exist in terms of phases and phase changes. You've been able to tackle this question and answer it. So let's read through the question. Figure 1, the graph shows the temperatures recorded when a sample of water was heated from negative 100 degrees Celsius to plus 200 degrees Celsius. So we're dealing with Celsius, not Fahrenheit. The water received the same amount of heat every minute. So the heat applied was constant. All right, so we've got temperature from negative 100 to 200 degrees Celsius. That's the scale on the y-axis. We have time in minutes from 0 to 17 minutes. And we have multiple letters associated with phases and phase changes within the graph. Question. Refer to figure 1 and answer the following question. In which phase does water have the greatest specific heat? Well, in this particular question, it doesn't look like we need this diagram right now. Very similar to one of our previous questions. So this question here may not directly source from the picture, but this is one of those situations where this picture probably has 2 or 3 other questions associated with it, which will use it. Okay? So in which phase does water have the greatest specific heat? Solid, liquid, or gas? That's pure reference tables. So if we look here in our reference tables for specific heat, here we go. Solid, liquid, gas. So which one has the highest specific heat? It would be liquid water. Let's take a look at the second question. When 1 gram of liquid water at its boiling point is changed into water vapor, ooh, it's a little bit of a tongue twister. It wants to know what occurs with the heat and how its environment impacts that. So when 1 gram of liquid water, so we're starting with 1 gram liquid water at its boiling point. So we're saying it's at the boiling point. So we're actually here in the diagram. So we've got liquid starting to boil, right at D in this curve up here if you just want to reference that. So 1 gram of liquid water at its boiling point changed into water vapor. Well, in order to change into water vapor, we've got to add heat. So if we're adding heat, we've got to choose one that says gained and not released. So it can't be choice 2, and it can't be choice 4 in this case, because it's gaining heat, it's changing to gas. Now we have to make sure we know that we're using the right value for our phase change. So if you're not sure, check to see which one of these results in evaporation or boiling. And that's vaporization, 2,260 joules per gram. And we've got a gain of that in choice 3. So we are at another place in our continued education online. Hopefully I've been able to answer a lot of your questions through our WebEx seminar. Hopefully I've answered a lot of questions just in this video. Hopefully you've had an opportunity maybe to comment at the bottom of this video, or maybe you've sent me further communication through WebEx or through Google Classroom. Hopefully, at this point, and now that you're probably about a week into this instruction, that you're able to kind of accommodate a new routine and it's working out for you. But again, thank you for watching the video, and hopefully this has had an impact, and we'll pick up with the next topic after.